Now we are going to continue our support vector machine topic. Okay, take a look at this figure. Okay, you can see that the reason why we use SVM net is because we can use a line or a surface to divide the data point of purple and green on two different sides, right? So the basic assumption is that we can use some certain line or surface to do such kind of classification. But there's one important thing that what if the data point we collect, which are not linear dividable? Okay, so here we have an example like this. We have green dot and purple dot, and apparently those data points are not linear dividable, right? So to apply algorithm like SVM is not feasible, right? Because the line would be very strange like this one. So we have several strategy to divide such kind of data points. The one is that we can create a line or a surface, okay, nonlinear line, which can divide the space into two different parts. But it is a little bit difficult for mathematicians to do such kind of model algorithm because we don't know what kind of line, for example, is powered by 2, 3, 4, 5, or any other exponential function can help us to model such kind of a nonlinear line to do such kind of classification. So we have another kind of thought, okay? That is, let's take a look at this one, okay? That is, if it is the original x1 and that is x0, we think about one thing. Is it possible that we can create a new dimension, which is z right here, and this kind of new dimension is possibly a function of x0 and s1. If we can create such kind of new dimension, and it will be much better, we can classify those data points in such higher dimension space. And as we can see that you can simply just draw a surface right here. Okay, the surface is like this one, and you can see that if it is a surface created by SVM, and we can see that the height between the surface, the SVM surface, and the support vector in green dots, and again we can, for example, that is the support vector of purple SVM, or purple support vectors. If we can divide these two classes of data points in a higher dimension, and of course we still use SVM because SVM is a very simple one. It is a linear algorithm. Okay, we can find such kind of SVM surface which can perfectly classify these two data points. Okay, these two classes of data points, and that would be better because linear algorithm SVM, which is simpler. So the question becomes that how do we find such kind of f function which can help us to add another dimension to the original data, which is original space, which is x0 and x1. Okay, so the problem becomes, how do we create such kind of dimension? Okay, so here we have an example like this one. Okay, so let's take a look at the left hand side. For example, we have a very simple data which has only one dimension, which is x0. Okay, and we have some data points right here, the green dots and the purple dots. Okay, so it is relatively easy for us to find such kind of boundary line of SVM. So we have the width between these two support lines, and we have x star value, which can divide two classes of data by using this x star value. Right, we can find this such kind of value in such kind of boundary line by SVM. But think about one thing: if some data is not possibly divided by SVM, such like the right hand side, okay, the green dots is right here, okay, we have purple dots right here. It is not possible for SVM to divide this such kind of data, right? So we think about one thing. We can create a new, for example, a new dimension which is called y, okay, and it is a function of the original space, which is x0. Okay, and let's make some assumption. Okay, we don't know which kind of f function it should be to separate these two set of data, but let's take a look at, let's make a try. Okay, so let's assume such kind of data could be, okay, something like that. And as we know, the blue one, okay, the blue function, it should looks like this, a curve, right? It should looks like a curve, right? That is this line. So if we map all the data point to find its corresponding y value, and we can see that the green dot has such y values, and the purple data point will be right here. So that means originally we have n data points, right? And every one of them is just in x0 dimension. But if we use a f function and max it to like this, or like this, we can create a new dimension right here or right here. So we can apply SVM in this new dimension. For example, something like this one. Originally in x0, you cannot apply SVM because it is not linear separatable. But if you add another dimension, which is y, it may be easier for SVM to perform such kind of to generate such kind of boundary line that can perfectly divide that point of two classes into we have into two different subspace, right? So it is possible. Okay, I would like to show you something like this. For example, if you have a data point, okay, it has only two dimensions, x0 and x1, and if you want to create a new representation of this data point using 3 dimensions. And as we know that the size of the vector is 1 times 2 and 1 times 3, right? So basically, if you use new vectors, which is 2 times 3, the size is 2 times 3, and you can map the original data x0 and s1 to 3 new values, which is x0 prime, s1 prime, and s2 prime. The only thing you need to do from the perspective of vector, you only need 6, okay? You only need 6 values, and then you can transform your data from x0, x1 to x0, 1, 2, 3 prime. And of course, we don't know, we have no idea what WS. So it could be anything in that matrix, in that matrix, 2 times 3 matrix. Okay, so it can it is just one of the candidate of f function that can map the original data from 2 dimensions to 3 dimensions. Okay, but we know that it is possible to do such kind of dimension from 2 to 3 dimension, and we can perform SVM on x0 from x0 to x1 x2 prime space. So the problem becomes, again, how do we find such kind of f function or such kind of w to help us to transform the original data from the low dimension to high dimension? Okay, so that is the concept of more advanced SVM. Okay, so before we explain how do we find such kind of f function, and we'd like to introduce several things. For example, this one. Okay, here A and B are both data point. A and B are both data points. So A and B can be represented as all its features. And we use a vector so A and B are data points or they are vectors. Okay, so when we write it in this way, that means dot product. We dot product these 2 vectors, A and B. And I think we can draw something right here. Okay, so for example, that is the x0, that is x1, and we have 2 vectors. Okay, one is A, the other is B. So when we do dot product of A and B, that means we do projection, and the value of A product B is exactly the length of the projection, which is right here. So that is AB. That is a value, that is not a vector. Okay, the A product B, A dot product B, that is just a value. It is not a vector. It is the length of the projection line. So think about one thing. If A and B are similar, or we say that they're very close, and then the value of the dot product will be large, right? So if A and B are not similar, which means they're far away, they're two different data points, and they're far away, then the value of the dot product of A and B will be small. So dot product is a way that helps us to evaluate how close A vector and B vector is. Okay, so that is the concept of this dot product. Okay. So before we continue to figure out what is the f function, there are some properties. Okay, I would like to explain. That is, if you x0 and x1 is your original space, and x01, x02, x00, x0, x1, and x2 prime, those are the new dimensions. So when you do such kind of transformation, is there any properties that we should keep? Although we can do whatever in this f function and this w weight to transform the original data point from two dimension to three dimension, but mathematics tell us that we should keep some properties when we do such kind of transformation. So the idea is that, okay, so we have dimension. So originally we have several data points, right? This one, and for example this one. Original we have n data points. Okay, we have n data points. Okay. Since we talk about distance or dot product, we can see that although there are only 3 data points in this example, but we have n equals 3, right? We have 3 pairs, right? We have 3 pairs, and each pair, it has a distance between 2 data points, right? So we say P1, P2, P3. So the distance will be distance 1, 3, distance 3, 2, distance 1, 2. We have 3 pairs of distance. When you do such kind of dimension, would you change the dimensions? Okay, so we have new dimensions, 3 dimensions, and those data points changes from P1 prime, P3 prime, and P2 prime. And again, we have 3 different pairs, right? So we have 3 different pairs. The mathematics tell us that if you change your dimension from 2 and up to 3, the property we would like to keep is that the D13, D12, and D32, all those distance in dimension, 2 dimension. Okay, so we'll write it in this way. Distance, okay, DIS means distance in 2 dimension. Okay, we have data point I and data point J. Okay, if possible, okay, we erase these things. Okay, if possible, the distance in the 3 dimension, okay, of Pi and Pj, and of course all Pi and Pj belongs to all data point we collect. Okay, so that is, it will be better that this distance is related to the distance at 3 dimension. So we can simply just write, for example, in this way. There is again an unknown function that we put the distance of data point in 2 dimension, and we can calculate all those distance, right? And we can use it as a parameter of a big F function. And the big F function, the result will be the distance of those Pij in the 3 dimension. So that means the distance is related. So that is the property we like to keep when we change our dimension from the lower dimension to the higher dimension. That makes sense. That means the relationship between each data point has a constant relationship, which is of course it is right now it is an unknown function, but we will figure out how to design such kind of big F function. So that it makes sense when we change our dimension from the lower one to the higher one. Okay, so that is the property we would like to keep. We would like to make the distance in the lower dimension and the distance in the higher dimension has certain kind of relationship, so that the dimension, if you upgrade to the higher dimension, that means the such kind of relation between data points can be sustained. Okay, so that is the concept. But how do we find such kind of big F function to do such kind of space mapping? Okay, so here we have this one. So we have a definition right here. You can simply just remove this one. Okay, we have a dimension. Sorry, we have a definition right here. Is this one? This K function. Okay, the K means kernel. Kernel function. So the X and Y right here, they are still the data point. Okay, that's still the data point. Okay, we use this data point as the parameter of the kernel function, and the kernel function is defined as the X will pass through a phi function, and the Y data point will pass through the phi function as well. So the result is called X prime and Y prime. So we will talk about the phi function later, okay? And we perform dot product right here, right? That is a dot product. So basically it means first we use the original data, which is X and Y, and we pass it through a function. That function can help us to find the X prime and Y prime, and X prime and Y prime is the data point at the higher dimension. And we use this X prime and Y prime to do dot product. That means we like to evaluate the distance between X prime and Y prime in the higher dimension space. So that is just the definition. So a kernel function is defined as we use the original X and Y and pass it through certain unknown phi function, and then we use the result to evaluate the distance between X prime and Y prime. Okay, so that is just the definition. Okay, that is just the definition. And we like to introduce 3 different algorithms of SVM. The first one is called linear kernel. That means, as we mentioned before, the kernel function should be defined as phi x and phi y, right? It's a dot product of phi x and phi y. But in linear kernel, it assumes that the phi function is a dummy function. It simply just output X and Y. Okay, So that is simply just a dummy function. Okay. So the result would be x and x dot product y. And what is that means? That means we don't do any changes to the original space. So basically, it's just a dummy one. So if you apply linear kernel on SVM, that means don't upgrade your dimension. You simply just perform linear regression on your original space, which is, for example, x0 and x1. Okay, so that is the first one, the very basic one. It's exactly what we introduced in the previous SVM algorithm. Okay, so let's take the interesting thing is the second one. Okay, is the second one. So again, what is polynomial kernel? Okay, again, right here, we can see that, again, this value should be equals certain phi x, phi y, right? And take a look at this one. So the purple part right here, right? That is exactly x prime and y prime, right? That means we want to evaluate the data point of x and y in a higher dimension space. So we use a dot product to evaluate the distance between x prime and y prime. Although we don't know how x becomes x prime, because it should pass through the phi function to generate the x prime data point. And we need to use y data point to use it pass through the phi function to generate y prime. So that is the y in the higher dimension space. And we use dot product to evaluate the distance between x prime and y prime. Okay, that is the definition, right? But we would like to define the relationship right here. So take a look at this one. That is the distance between x prime and y prime in the higher dimension, right? And take a look at the pink one. That is the distance between x and y in the original space, right? That is a dot product of x and y, okay? We wish, so that is the definition, right? We wish the distance relationship should be polynomial. That means this value plus a constant and power by degree, d. We wish this relationship sustain when we transform our data to the higher dimension. Okay. Although we don't know if it is a correct way to model the relationship of distance, but we wish it could be like something like this. Okay, so here I use example, a real example right here. Okay, so let's assume that d equals 2 and c is 0. So that is the simplest way. Okay, that is the simplest way. Okay, that is 0 and that is 2. So again, the kernel function looks like this, right? So the x, y plus 0 power by 2, x, y, that means x1, y1 plus x2, y2. Or you can write it in a more vector way. So that is x transpose dot y square. That they all represent the same thing. Okay, so that result is right here. So again, we'd like to show you that x is a data point. Okay, it has two features, x1 and x2. Y is another data point. In original space, it is y1 and y2. So we simply just, again, okay, here's the result. That is the distance between x and y, the distance value of x and y in higher dimension, in three dimensions space. Okay, and as we mentioned, we defined it as something like this one. So mathematicians is so smart, and they help us to do such kind of things, and they tell us that the five function should be looks like this. So take a look at this one. Because these two are that is x prime, right? That is y prime. Okay, so the new dimension, okay, the new dimension right here, it should be x1 squared. The second dimension of the new space is x2 squared, and so on and so forth. And this one is the third dimension. So by dot product x prime and y prime, okay, you simply just this one times this one plus this one times this one and this one times this one and plus it together. It should be this value, and this value is exactly this one, so that we can create such a relationship of distance in 2D space and 3D space. Although we don't know if such kind of polynomial assumption is correct or not, but we can do so. So by using such kind of things, we can we can transform our original data, which is x and y, using this value in a three-dimension space. And the relationship between all the data points, n data points, okay? So we have n data point, right? And we randomly select two of them. This function, this formula, still sustain. That means we pick any two data points in the three-dimension space, and its distance, okay, its dot product value should be the distance when they in two-dimension space with a square value. So that is how we use such kind of kernel function to help us to do such kind of transformation from two-dimension to three-dimension. Okay. Oh, so that is one of the interesting things I'd like to share with you. So and again, we model the distance of those data points in three-dimension, two-dimension by using assumption of polynomial, right? And again, we can have an even more complex relationship. Okay, so but it is a little bit difficult. So let's take a look at this one. Okay, that is a very complex relationship, right? The x minus y and these two, that means the distance in 2D. And the kernel function, okay, it should be the distance in 3D. And its relationship is exponential. And there is a parameter right here, and it is the distance. It looks weird, but that is mathematical design such kind of relationship between the distance of 2D and 3D. And let's take a look at why they do such kind of design. Okay, So I think it's right here. Okay. So before we explain why it looks so complex, okay, we will talk about Taylor series. I believe you learned those things when you are in high school or right or college. Okay, so that is the definition of Taylor series. Okay, and it is an infinite series. Okay, that is an infinite series. We can write it in this way, which is the same. Okay, so think about one thing that if a is 0, okay, we simply just put a is 0 right here, and the f function f function right here, we use an exponential to replace the f function. So the final result of the Taylor series, if you use it to express e and power x, the result is that is just a formula. Okay, that is just the formula. Okay, so think about one thing. If the kernel function we write here and the mathematician tell us that it should be defined as this one, okay, and we further do some calculation, okay, this one is exactly as this one, okay, and we put all the x squared and y squared right here, and the result would be here we have another one right here. Okay, so this purple part, okay, it is something exactly the same as this purple part because of the Taylor series. Okay, because of Taylor series, it is the purple part is the same. Okay, and we put the red parts right here. So again, take a look at this one. Okay, if this number, if this value is exactly the kernel, the value of the kernel function, it should be something like this one, right? So mathematically they are so smart, so they tell us that if we have a phi function, and you can simply just represent it as this one, okay? And you can see that this one and this one dot product this item and this item, and it becomes this item. And again, this one, this one, this one, and this one, it becomes this one, and so on and so forth. So on and so forth. Because this Taylor series is symmetric, so we can easily find the phi function of x. So phi x and phi y, if they dot product together, the value will be the same as the Taylor series. So that is designed delicately. So we just simply just use it, because in this way we can transform our original data, no matter what is the dimension, to almost a very high dimension, because it is a infinite series. Okay, so we can transform it to 10 dimension, 20 dimension, 200 dimension, 1000 dimension, which is okay because we can write it in an infinite way. So that is another way we can transform the data from low dimension to high dimension using RBF kernel. And if SVM cannot perfectly divide the original data in k dimension, and it's okay. We can further use k plus 1 dimension to test if SVM can divide the original data point in k plus 1 dimension, and so on and so forth, so on and so forth. Of course, currently we don't calculate all this value by ourselves. We use package. So package will tell. So again, I think right here, if we use package, which is support vector classifier, okay, we can assign different kernels. For example, that is RBF kernel, and then we can divide those two data points in higher dimension. And again, there will be some support vector right here. And there's some support vector right here. So this line, although it is drawn on the two-dimensional space, but think about one thing. There should be one surface which can perfectly divide the green data point and the purple data point in high dimension. And we simply just plot those surface back to the x0 and x1 space. So it is not a line. It should be a curve or something. So that is the support line. That is the support line. And we can find all the support vectors on the support line. And we can find the boundary line, which is the blue one. Right, because we map it back to the low dimension, so it looks weird. It is a curved line. But it can help us to divide those data points perfectly in high dimension. So I think that is the concept of kernel, that we can map our original data to high dimension. So and again, so right here, you can simply just assign different kernels to the support vector classifier. So here's the result. Okay, if you use linear kernel, you cannot divide those two data points. But if you use RBF kernel, it will transform your data to a higher dimension to perform SVM. So that is the polynomial kernel, but it has only the degree is 3, which is still not good enough to classify those data. If you make it 4, 5, or 6, it will be better. Okay, so again, that is the SVM with the concept of kernel, which can transform data to the higher dimension. So and again, when you use SVM, there should be a parameter called C. That is the margin. Okay, so that is the margin, because sometimes we cannot find a very perfect line to divide these two data sets. So C could be viewed as a tolerance or margin. Okay, so if you have a, so that is the result. If you have a small margin, that means you tolerate some misclassified data points in your margin. But if you have a larger margin, that means you tolerate some misclassified data point in your width. Okay, we will talk about the value of C later. Okay, so I think that is what I'd like to share with you about the kernel of support vector machine. Okay, and we will show you how to use Orange to perform SVM later. Okay.